Hi, welcome to 3.4, combining transformations of functions. So what we're going to be combining are some of the things that we learned already in this chapter. We've already learned about multiplying or stretching vertical and horizontal, and earlier on we learned about moving left and right. Before I start writing down some stuff, let's take a look at our getting started here. There's two different transformation images of the graph. Y is equal to the square root of x. Write an equation for each transformation image. So if I'm looking at this one, okay, here is my original y is equal to root x, and they give me two corresponding points, and then they give me two corresponding points on the image. So one thing I notice is that this corresponding point moves 1, 2, 3 left and 2 down, and so does this one, moves 1, 2, 3 left and 2 down. So when I'm looking at this first example here is just an example of translation. There's no scaling going on. There's no multiplying of the x and the y. So this is a translation. In fact, maybe I should just put this out. If you've got a transformation, there are different types of transformation. So the first type of a transformation is a translation. So what a translation is just moving up and down or left and right. So up, down, and left, right. And then we really have, you can call it scaling. Or another way of talking about scaling is compression and stretches, right? So you can have vertical stretches, vertical compressions, horizontal stretches, horizontal compressions, and also you can have reflections. So those are our different types of transformations. So when we talk about transformations, we're talking about all these different things that can happen. So maybe under scaling, I'll just write stretch, and compressions. So those are our different types of transformations, and we're going to put them all together. So in our first example, it's just a translation. So it seems to me it's going left 1, 2, 3, and it's going down 2. So we need to write an equation for this. So if we remember from our initial lesson, I think it was 3.1, if I'm starting with y is equal to square root of x, to go left 3, I will write an x plus 4, because if you recall, we would say the left and right is inside of the function beside the x, and it's x minus h. And so if you have minus 4, would be moving it 4 to the right. We want it to go left, left 3, don't we? We want to go left 3, so I'll put a 3 over here. And then we want to go down 2, so we put a 2 over there. And one thing the textbook likes to do, they like to say y plus 2 is equal to the square root of x plus 3. They do it slightly different. Okay, so that's the first piece we'll take a look at. And then how about this one over here, our second example? This is a bit different in that it's not moving left and right. It's not translation. This is going to be an example, I think, where it seems to me the y values are getting multiplied. So here's my original one, y is equal to square root of x. This point doesn't move at all, but the corresponding point here is halved. Right? Instead of the y value being 2, now the y value is 1. So really when I'm looking at this, I'm thinking the y values are being multiplied, or y values multiplied by a half. So y would be equal to, now if I do something inside of the function where the square root of x is, that affects the x. If I want to do something with the y values, I would put it outside of that function. Put it outside like that. So this would be my answer for the second one. So I kind of like this format. This would be my answer for the first one. So just to put this all together, I'm pretty happy with the Pearson did a nice job in putting together this kind of little applet here. So this would be my first example, the first example where it got shifted over to the left and down, but I think, how much was it? Let's just see. It went left 1, 2, 3 and down 2. So let me change this slider. So this one went left 3 and down 2. Okay, so you can see here is the transformation. They say y minus k. Now, I'll just write this for a second. I kind of prefer, instead of having a y minus k, I put the plus k over here. All right, but you're going to have to get used to this because that's the way the textbook does, and this is the way that I do it. But you see, mathematically, it's exactly the same. So if your k value is moving it up and down, if your k is minus 2, then it drops 2. So if it's on this side, you would say minus 2. If you put it on the other side, it would end up being plus 2 because minus negative 2 is plus 2. So you'll see how that k value moves it up and down. All right, and now here's your h value moving it left and right. If these values are 1, a and b are the multipliers, right, and h and k have to do with the translation and move it left and right. So if I want the function to be unchanged, then a is 1 and b is 1 and h and k are 0. And I can switch to these other different ones that we know. These are the parent functions that we know already. Y to the x is a diagonal line. Here's our parabola. This would be what we were working with grade 11. So this looks more familiar, doesn't it? So the h and the k, move it around, and the a, if it's negative, we would say it opens downwards. Now in grade 12 we would say it's reflecting on the x-axis. Okay, and we talked about these rules earlier, about what each of these things do, so I won't go over them individually, but you can see that what we've done now is we put them all together. What I should mention here, so first I'll write it down the way I would write it as a function here. I could say y is equal to a multiplied by the function, and then b x minus h plus k. So here's just sort of, if I want to just call it a function, I can call it function f and put it like this. And then if I pick one of the functions, I can pick any one of those. What was I going to say? The order in which you're going to apply these is that you would do the a and the b, you would do those first, and then you would do the h and the k afterwards if you're going to take a function and then graph its image. Let's go over and work through our book here. Okay, it says in the same grid, sketch the graph of each function below and then describe its transformation. Okay, so here is my parent function. So my basic parent function looks like this. Y is equal to the absolute value of x. And let's try, if I go and apply my letters using that absolute value, here I'm going to get b x minus h plus k. So now instead of using the function like f of x, I'm actually putting the absolute value. You can see that the things that are associated with x are inside the function, and the things that are associated with y, a and k, are outside the function. So a is how much vertically it stretches. B is how much horizontally it gets compressed and stretched. And remember, you have to do the reciprocal of b. So you got to make sure that you would divide by b or multiply by 1 over b. H is what moves it left or right, which is x related, and this moves it up or down. So if my original point was x comma y, that would correspond to my new point. Now let's make all these changes. X becomes x over b because it gets divided by b plus h, comma y now becomes ay plus k. So that becomes my new point. So from here to here, what happened? Well, they added that 2. Where would that 2 belong? That would be a b, right? So this would be b is equal to 2. So what does that change? How does that transform this one over here? So I'm going to be taking all my x values and dividing by 2 or multiplying by 1/2. So all my x values are getting smaller. So you can imagine what happens is that it compresses. So we're going to get x values multiplied by 2 which causes a horizontal compression. Now from this step to this step over here, now we have 1/4 that's been added. So that 1/4 would be the A value here. So we have A is equal to 1/4. So my Y values, oh, you know what, I made a mistake. X values multiplied by 1/2, right? And that's why the X values are going to get smaller, and that's why it'll be a horizontal compression. Now in our second one, my Y values are going to be multiplied by 1/4. And so whenever you multiply the Y values by something smaller than 1, the Y values are going to get smaller, so we're going to get a vertical compression. Now from this step to the next one, we'll try red now, we'll just switch it along. What have we done? Well, we've added this +3 part. Well, this would be this value here. So we could say H would be equal to -3, right? Because it's minus H, so this must be subtracting a -3. So that would be shift 3 units left. Okay, I just want to note, and I'll bring this to your attention later on, you'll notice that the H has to be inside of brackets. So this, another way of saying it is this 2 has to be factored out. So if you had something like 6x plus 2 inside of the function, so like this, for example, in our example here, you would switch this to y is equal to the absolute value of 2. Oh, sorry, you would do the absolute value of, factor out a common 2, and then we'd get x, sorry, we'd take out a 6. I'll back up. That's not a very friendly example. I'm going to switch this 6 into 2. 2x plus 6. Let's say if we had 2x plus 6, you'd factor out the 2, and we'd say x plus 3. Like that. So in my made-up case, the H value is -3, and our B value is 2. So we don't use this 6 here. We have to factor this out because we want just x plus or minus something, and then multiply it afterwards. Okay, so back over here we have an H of -3, and our last step. Oh, I guess we'll go back to blue. We've added this 4. So this K is equal to 4, and so we get 4 units up. So describe how the graph of this is related to the graph of this. Well, if you start with the original graph, which I've done kind of poorly, you would go through these steps. You'd say, first of all, multiply all the x values. Because of this, multiply all the x values by the reciprocal of that, by 1/2. Now multiply all the y values by not the reciprocal, but the exactly 1/4. Now move everything over 3, or another way of saying it is subtract 3 from each of your x values, and now add 4 to each of your y values. Okay, this, which I hope you've written down, will transform each of the points from your original graph to corresponding points on the image graph. You know what, let's go to our first example here. It says applying a combination of transformations to the graph of a function. So this original function here is the same as the one in blue here. So that's this, you know what, I can do better than that, is the same as that blue one. I'll leave it uncolored for now. And now we see they draw 2 other ones. Okay, so we want to do a horizontal compression by a factor of 1/2. So in other words, horizontal means x. So my x values, in order to get compressed, they're being multiplied times something less than 1. So they're being multiplied by 1/2. So here's an x value of 4. You'll see now this is an x value of 2. So this original one gets compressed and turns into this one here. So the blue, I'll outline in blue. not that well, but I think we're getting the job done. That is after just this first transformation of a horizontal compression by a factor of half. Okay, now the second one is the translation of 3 units left. See this piece here, it moves 3 left, 1, 2, 3, and goes here. So this blue one gets transformed 3 to the left, and then we get the green one over like that. So originals in black, the compression by a factor of half is the blue, and then moving left 3 is the green one. Or you can do it with the table of values. You can take a look at each of these 1, 2, 3, 4 table of values, and then here is, they just do the first transformation, don't they? They're saying, okay, we're going to be keeping all the y values the same. This 3 stays the same, that 3 stays the same, but the x values, because b is 2, we're going to be multiplying by the reciprocal of 2. Multiplying by 1/2, or another way of saying it is to be dividing by 2. So this -4 turns into -2. This 0 divided by 2 is still the same. That 2 turns into 1. Okay. What they don't do is the next part, just below it, if I was to erase all my drawing and scroll downwards a little bit, you'd see they say, now just move it over left 3. But why don't we add another part? We could say y is equal to f2 of x, 3 units left. Oh, actually I have to put that inside. 3 units left would be inside there because that's a horizontal change, so it would be x plus 3. So that would be a point on this one. So now I would take all my x values and say subtract 3 from them. So 2 minus 3 would be -5, comma 3. 0 minus 3 would be -3, comma -2. And 1 minus 3 would be -2, comma 5. And 2 minus 3 would be -1, comma 2. Now that gives me all the points on this green line. Okay, I'd like you to give it a try. Try to check your understanding. I'll just do a pause for a few seconds, and then I will show the solutions. Okay, hopefully you did all right on this one. They do a vertical compression by a factor of 1/3. So the vertical compression that multiplies all the y values by 1/3. And I think that's what they do, the x and the y, and see each of the y values get multiplied by 1/3. But my x stays the same. And then the translation 2 up, again, they don't do another column, but you could easily do another column and say, now take the y values and add 2 to it. So you could do another column, and instead of -5, comma 1, it would be -5, comma 3, and so on. So you do that. And they don't really give a nice sketch of it, unfortunately. So I'm just going to be moving on. If you have any questions, ask me. So here they're putting it all together, and we've seen this a few times. So in the graph of y minus k equals all this, now you'll notice, or you can say y is equal to all that plus k, either way. A horizontal stretch or a compression by a factor of 1/b. Okay, so if this is some number, say 4, then you can say I'm going to multiply by 1/4. And now just remember that multiplying is the same thing as, or multiplying and dividing are reciprocal functions. So if b is equal to 4, right, you can say, oh, I'm going to be multiplying by 1/4, or another way of saying the same thing is dividing by 4. Okay, let's say if b is equal to 1/3, you can say I'm going to multiply by the reciprocal of that, right, or I'm going to be dividing by 1/3. Okay, so clearly in the case of a value of b which is greater than 1, it kind of makes it easier in your head to say, oh, I'm going to divide by that 4, but in the case of something like this, you can say I'm going to multiply by the reciprocal. So it's easier to do with the whole numbers. But just remember, the b value, you can either think I'm multiplying by its reciprocal or I'm dividing by that value. The a is just straight ahead, you're going to be multiplying by a. So you don't have to worry about that reciprocal or that dividing nature. If this b value is negative, then the x values would be multiplied by a -1, so it reflects over the y-axis. So that's why we get this. And same thing here for the a values. If the a values are negative, then all the y's will be multiplied by -1, and then you get a reflection on the x-axis. And this one is a very good thing to remember for your general transformation. Okay, so I hope that's working out for you. We're going to reinforce that later on in class. Example number 2, use the general transformation to sketch the graph of a function. So here they just give you a generic graph, and they're going to say, okay, sketch the graph of, if this is y of f of x, now make all these changes to it. So the first thing you do is when you analyze this, you compare it with y minus k is equal to all this kind of stuff, and then just list what is k, what's a, what's b, and what's h. So here you see k is 6, a is 1, b is 4, and h is -2. When you're doing these transformations, save the translations for last. Do the a and the b parts first, and then do the h and the k afterwards. Okay, so the graph of is horizontally compressed by a factor of 1/4. So this b here, that's the horizontal compression. So in other words, you take all the x values and you can multiply by 1/4, or another way of saying it, just like we said before, is divide by 4. The y values are going to get multiplied by 1, so they're not going to change, no problem. Once you've done that, then you can take a look at the h and the k. So the h means that all the x values will be 2 will be subtracted from them, and all the y values, 6, will be added to it. So we can pick a bunch of points from the original. They've got 1, 2, 3, 4, 5 points, and they do all these changes here, right? They say, okay, if you have x comma y, you're going to say x over b plus h, that's where this part comes from, x over b plus h, and then the y plus 6 comes from this a y plus k. It's just y because a is 1. So if x comma y is the point, take all those 1, 2, 3, 4, 5 points, list them here first, and then you're going to say, okay, x minus 4, x divided by 4 minus 2, in this case it would be -4 divided by 4 minus 2, and that gives you -3. 12 is the y, so 12 plus 6 is 18, and so on. So you plug each of this -2 into this, and you get that. You plug 0 into here, and you get that. So you do that work, and then you sketch it. And it should have all the compressions and the translations done for you nicely. And then they state what the domain and the range is. Okay, so I will do something similar here. I'm going to ask you to try number 2 to check your understanding, and then to state the domain and the range afterwards. I'll just do a little bit of a pause, and then I'll show the solutions. Alright, so hopefully you paused it and then did the work. Let's take a look. So first of all, analyzing this and calculating what the k, a, b, and h are. -4, 1, a half, h is -1. And here are the values. Unfortunately, they don't give me a sketch of it afterwards, but you can compare this table of values with your table of values. Alright, moving on to the next page. Example number 3 is transforming the graph of a radical function. So here we're starting with our parent function. In this case is y is equal to the square root of x. So if they want us to graph this, what are the domain and range? So we have the y is equal to the square root of x, and then comparing this with our form y minus k and all that, you can figure out what the values are. K is -1, a is 2, b is -1, and h is 3. So again, do your vertical stretches and your horizontal stretches first. It's vertically stretched by a factor of 2 because a value is 2. Horizontally, it's going to be multiplied by the reciprocal of this or divided by that. So really the only thing that happens is a reflection and not a compression or a stretch, because it's just going to be multiplied by 1. So that negative will cause a reflection in the y-axis, and then you get it translated. We get 3 units to the right and 1 unit down. So you can pick a few of these spots and then do the translation. So 00114293, you can see you plug in an x and y becomes the square root. So pick x values that are squares, all right, and then make this translation where you get negative x plus 3, so negative 0 plus 3 is 3, negative 1 plus 3 is 2, and so on. You figure out your x values, figure out your y values, and do your sketch. Okay, and once you got your dots, then you can make a nice smooth line and then state the domain and the range. I'll leave you to check your understanding. And the other thing is, if you want to check something like this, if you switch this into y is equal to negative and the square root of 3x plus 3 plus 2, you can throw it into desmos.com or geogebra.org and have that graph for you, and it's a very easy one for you to check. I'll just show you. I'm guessing that they don't even hit show solutions. They give you a table of values, but I don't think they actually sketch it for you, so you would have to go and check that yourself. We can do that later in class if you'd like. We've got one more example here, the example number 4. And let me check, is that actually, yeah, that is our last example. So this is the one which is actually something a little bit new. It looks a little bit complicated here. I'm going to look it over, so I'll be right back with my next video in a second.